Mm-hmm.
So this is the heat conduction in a cylindrical rod, and these what's called phases at t equals to 0. Here t equals to 0. So what he said here is this is a cylindrical rod with a diameter of 0.05 meter. I don't think we even use this. And the length of 1 meter. And initially it was heated to 100 degrees C, which means if we write down the boundary condition, initially whatever the x is 100 degrees C. And then, because these two sides, he said, are kept at 0 degrees C, so whatever the time it is, at x equals to 0, it becomes to 0. And whatever the time it is, when it becomes to L, which is 1 meter, it becomes to 0. So here are the three boundary conditions we consider. Then he asked to carry out a heat balance on this element. We went to Goody's office today, and he told us that mass balance and heat balance is definitely what he not in the exam, but definitely you need to know about. He said it's much easier than the momentum thing, so he may not ask too much about momentum, but heat mass transfer is definitely the same. Okay, I'll try to write here. And for here, we want to carry out, let's say, from here to here, with x to x plus delta x. And we say, because, say, it's not steady state, so you may have the temperature rising of this rod, and you have heat flow in and heat flow out. So when we say, we know Q equals to minus K times partial T over partial X. Whatever the flow, it just goes like this. And then you have the like this. You have the Q in minus Q out. This gives you the accumulating. Basically, it should be BQ. So BQ in minus BQ out should give you BQ accumulating.
Why
So,
it is big Q?
Because small q means for unit area. It's just for unit area. It's fine for this question to whether you're using the big area or the big Q or small q, because if you are considering for unit area, that's the same. But if you are considering about heat loss to ambient or atmosphere, what you get accumulate here should be equals to heat loss here. And in that sense, when you're considering about per unit area, it's not the same as the unit area. It's about the
Total.
However, I don't know English. I don't know English. Anyway, so let's go. And Q in minus Q out becomes to Q in is minus I say Q in minus Q out, you can say is Q in plus partial Q over partial X times it's called sigma or whatever. So heat come in heat goes out equal to what comes in plus how fast it changes in this distance and how long the distance is. And what you get from here is minus partial Q over partial X times this. And if you plug that in, you will get A times 2K times 2 partial square T over partial X squared, because here you do the partial differentiation again, times So this is Q in minus Q out. It comes to here. By boundary conditions. And then we consider about heat accumulation, which is the mCp delta T. This is how it goes. Then so it becomes to rho of the material times A times delta X, that is the mass of this, and times Cp times, because here we are considering about Q is the rate of the heat flow, so you have temperature change with time. And the thing is, you make this equals to this, and cancels A, X, so you get partial T over partial X, partial T equals to K over rho times Cp times partial square T over partial X squared. So by now we have got the equation for us to solve, and this is the result from our heat balance. And we usually we say this, we can say this part, give it a name called alpha. Yeah. So it's really nice and tidy. And the thing left then is PDE. And to solve this, we just define T is a function of time and X. So we'll say T is a T could be the product of two equations. Two small functions. So T is the product of two functions. Not Tx, right? Not X. So T is a function of time and distance. And then in this way, partial T over partial small t becomes to T dash, I'll just write T dash here, times X. And partial T over partial X will become to T times X dash. And if you do again, differentiate again, just call 2 dash. So it looks like that. And when we apply this to here, we'll get T dash X equals to T X dash dash times alpha. Okay, and I'll just clean all this. So here is the final equation we would like to solve. And to make it, to arrange it, we will get the equation like T dash over T equals to X 1 over alpha as X. Normally we just put alpha to left hand side because this here we got second order, here is first order. So kind of feels it is relatively easy to solve. And applying what we learned from PDE, what we get here, we can make this become to a constant value. We call it minus lambda squared. The thing here, minus, is to provide a mathematical solution. If the value here become to 0 or positive, you can hardly find a solution for mathematics. For mathematical or physical realistic solution for this equation. So just remember, you will always have a minus lambda squared here. And then it's the same as what we have seen before. So you have, let's put it to, first we would like to solve function of small t, and then we have 1 over alpha times t dash over t equals to minus lambda squared. And t dash is dt. No, let's say the function t. Let's see, how do you say that? The function t over the variable equals to alpha minus alpha lambda square. And here you get t. Clear?
Oh.
Yeah. Okay.
Is that a big Q?
No. It's 1.
Oh,
Sorry for
okay,
that.
okay.
T function. That function of t dash is the differentiation.
Yeah.
Deviation.
No, the differential equation of function t. No, I
Function
didn't
t.
give it a good name. Let's say we call it here. I don't want to. I don't want to.
Yeah, that's fine. But that is a function.
Yeah, so here is a function. Here is also a function. Here is also a function tf.
D. Could you write down that function? What is that function?
Yeah, we don't know the function yet. We
No.
want to solve this function.
Oh, but that is a function.
Yeah, so you can say, let's call it, for example, y. So it becomes to y, dy over dx equals to minus alpha lambda squared. So we said tf is a function
Yeah.
of time. So we just call tf is kind of like y
Yeah.
in normal mathematic way, and dy over dx.
Okay. And t dash is something like
T dash is dy over dx. It's the differentiation. And then we have just shown the solution for this. If you have things like this, you will get Tf equals to a times e to the power of minus lambda square t alpha minus alpha square. Yeah. Sam, do you understand this now?
Yes, thank you.
Sorry.
This is what we just solved before. If you,
Oh. Let
you
me see.
understand? No, you don't understand. I'll write down for you.
Yeah.
Dy over y equals to minus alpha lambda squared times dx. This is exactly the same from this one, right? And then you do the integration both terms. You got log y equals to minus alpha lambda squared plus c.
Plus c.
Plus c is the constant you always get from integration.
Yeah, you integrate it.
I integrate both
we
sides.
there should be an x on the.
Oh yeah, sorry.
Yeah.
You get correct.
Oh.
You got x, and then you get y equals to a times e to the power minus alpha lambda squared x
And c come to the front as
from
a.
a. So this is what you get. Tf equals to the a times e to the power of minus alpha lambda squared x on t. So that's the first part. We just leave it at this moment now because we are not considering about boundary conditions yet. And now we are solving the second part, which is x dash dash over x equals to the minus lambda squared. Remember the solution for this is x, say x function x equals to a times cosine lambda x plus b times sine lambda x.
Let me see.
Remember?
Oh, can we find this in the formula sheet?
Yeah. In the previous, I think 2 years ago, he provided this, and you can just go and check for it. But just remember it. It doesn't hurt you. And if you want to go to the detailed solution, you can go last year's Mice and Guta's lecture, and I think you can find it.
I think Budi should provide us with this.
He mentioned this during the lecture, and I don't want to go into detail with that.
Yeah.
So that's fine. And then we have both two functions, and we can consider about boundary conditions now. We said the first boundary condition is when t equals to 0, and t equals 0, whatever the x is, the same. The rod is 100 degrees C, but it seems that we have too many things to solve, so we cannot solve that now, and we'll just deal with the two other boundary conditions. So one of our boundary conditions is t0 becomes to 0. And when we consider that just t, whatever the t is, the thing is 0, means this function must to be 0. Because if here is 0, that means this equation has trivial solution, whatever you call it. Trivial? Yeah, that's solution.
Wait a moment. Let me see. T is like the.
Let's say t equals to x times t,
Yeah.
right?
Yeah.
If you want this, whatever the x is, when x comes to 0, so x equals to 0,
Mhm.
whatever t you take, this has to be 0, which means here
Yeah.
should be 0, rather than here to be 0.
Yeah.
Right. So the problem becomes to finding the kind of condition when x comes to 0, this equation comes to 0. And when x comes to 0, because sine 0 equals 0, so this term disappears, and what we got is here. So if this equation wants to be 0 at lambda times 0, so cosine 0 will give you 1. So a times 1 comes to 0. A has to be 0.
Which one? Oh,
Yeah.
cosine
Yeah,
0.
I'm following.
Cosine 0 is 1.
Just subbing 0 for x.
Why cosine 0 is 1?
Cosine 0 is 1. Cosine 0 is 1.
That should be. Oh, yeah.
Cosine 0 is 1, right?
Sine
Yeah.
0, 0.
So 0 equals to a equals 0.
Yeah. So
Yeah.
you don't have that term then. And the other one is t1 equals 0. That is t when it reaches this point, it's still 0. So when we're thinking about 1, if I put 1 here, it becomes to sine lambda equals 0. In that way, means lambda has to be n pi. So sine n pi is 0. Either you get
What
it
does
back.
does the cost disappear for that one?
Yeah, because we got a equals 0.
Oh, of course, yes. Yes, that makes sense.
So lambda becomes to n pi. And now we have solved two variables, lambda and a now, and we just put everything up together. So we get t equals to a times b. We just call a new variable a dash. This is the product of a and b times e to the minus alpha lambda squared t times sine lambda x. This is the almost final solution we would like. And lambda we just solved becomes to n pi. And it seems that we only have one variable left, so we can apply the very last boundary conditions, which is when t equals to 0, t becomes to 100. And that means this a times sine lambda x is 100. At this point, we can try to, because here lambda equals to n pi, and for each n you have a solution for this equation, and we just do it in this way.
For each n.
Let me write down like this. For a times sine n pi x. You have a lot of n here, and because it's a sine wave, and according to kind of fully that whatever Fourier said, basically you can get an equation to describe this 100 to become equation of, if you want to describe it in a sine way, because what we get here is sine, and we need to go for the Fourier transformation of 100 to make it become sine, and then we can equate the both sides and get the final solution. So we get, according to Fourier transformation, 100 we can express this in n pi x. So this is Fourier transformation. You find a function to describe the 100. Ignore that part. So this part equals to 100. And 100 could be expressed in this way.
Yeah.
So this equals that.
Okay.
Yeah.
But why they need to add all of them together, sum all of them?
Because if you consider it's a sine wave, if this point fits, then this point fits, this point fits, this point fits, this point fits.
Yeah.
So all of them are the solution.
That's why you have n. And it repeats, right?
Yeah. So we just have them all here.
But in real condition, how do you do the calculation?
We don't really need to do calculation. Fourier has the solution for this, and Budi gave this in the formula sheet. So
Yeah.
he gives all the Fourier transformation for both sine wave and cosine wave. And the thing is, we need to solve this in the sine wave. And according to him, if you get a sine wave, you have an, and an equals to 2 over L from 0 to L, and fx times sine n pi x over L dx. And fx is the function you get here. So this is fx. So this is fx. We just put it down here. I just clean this. And this is the general form. And in our question, our an, because here we have L to be 1. So what we get here is 2 times from 0 to 1 times 100 here, sine n pi x. I think Budi's lecture ends up here, but I asked him about the solution today, and he did further. So which means we need to continue the problem, doing the integration. And for this one, it becomes 2 minus 200 over n pi. I think
Is this using Fourier series?
Yeah.
Okay.
And
No, that is the Fourier series.
yeah, we are trying to find the an now.
And
It's 200 over n pi, and this then becomes cosine n pi x from 0 to 1. And when the things becomes to 1, this becomes cosine n pi. When things becomes to 0, it becomes 1, so cosine n pi minus 1. But here we got minus sign here. So this finally becomes to 200 over n pi times 1 minus cosine n pi. So this is what we get for an. And then we can very happily, no, I'm not happy, and to say t equals to e to the power of minus lambda squared times alpha times time times what left there should be the a times sine n pi x, and we said that this, because this equals to that equation or some to 100 or something, and then we express them in this kind of form times, so it becomes to an times sine n pi x, where an equals to that's the end.